Bom dia, good morning. So let's continue with studying numerically the interface instability. And I would say for this course would be numerical study of a singular right? Because you don't have to necessarily know about fluids, right? So we studied. So let me show you so this is the system we're trying to solve numerically. Let me refresh our memories. Okay. Because I'm going to put because I'm discussing both, some numerical diff. Okay, I'm going to discuss two with you. Let's see what else I want to say. So as a reference, right, this is a paper which was my postdoc SIAM Scientific Computing 98. This is a SIAM journal. Okay, but you don't have to look at all the details. Understand this is for people who are interested. Let's see what else. Okay, I have in a figure, so I have. And I'm going to put this point here because I do not need, as you will see, when I impose numerical boundary conditions, periodic, sorry, this is the same as this one. So this, let me leave it open just to indicate. Okay, so this basically has periodic condition. What else do I want to say? So this, in the, let me see. Yeah, in the paper, let me use now the notation of the paper we're calling E0, E2 pi, which is the same as S0 as 2 pi. Okay, so we follow the notation of the paper. H. Two pi over n, right? And Ej is JH. Okay. And I think with this formula, and let me just remind you of something else, and we have also from our linear stability analysis, we have this. So I think these are the ingredients we need to have in mind, which is this surface tension equals to 0, surface tension different from 0, this is K. Here we have a K star, which is a cutoff, and this is our lambda. So if I write this on the board, do you know what I'm talking about? Right? I think so. Right? You don't have to remember maybe all the details, you know what I'm talking about. And maybe it's a cultural thing too, I forgot to mention. Maybe let me write it here. This is just a cultural thing from fluids. I mean, you don't have to even worry about fluids. Sometimes this appears like this. It's called a Weber number. So it's when we do differential equations, particularly in asymptotic analysis or on the computer, it's very good to have do dimensional analysis, have some reference numbers which you can play with. And in this problem, one net reference number that appears is called the Weber number. Depends on surface tension over density, the speed of the shearing. And if you put it here, you remember that if the Weber number, there's a critical K where this becomes imaginary, and therefore the eigenvalues above this value are imaginary. So this here, if you want, I can call this the real part of the eigenvalues. If it's real, right? So for example, if surface tension is 0, which was the problem that Krasny did, which is the problem that Moore did, right? If surface tension is 0, the Weber number is 0, the eigenvalues are real and grow in unbounded fashion. That's why the problem is ill-posed. The linear problem is ill-posed. High Fourier frequencies grow with an unbounded rate, right? And that's what Krasny did, the Krasny filter, right? To take these guys out of the dynamics unless they became active in the dynamics through nonlinearity in a genuine way, okay? So, okay, ask me questions if, from last week if you don't remember. So this is like a generic, I might say, generic system of equations that I'm going to solve. I've been vague on purpose so I can play with this together with you in a different way and remind you of things. Okay, so why am I being vague? Particularly because of the integral. I'm subbing over m, right? I'm not telling you how I'm summing this. So let me remind you some things, okay? So right here I'm being vague, just so that you make this clear. So look, if I do, let me do a little reminder, m over all points different from j, do you remember who used this integral? This singular numerical singular integration? Krasny used it, okay? So Krasny, you just skip the point where the integral blows up, right? And Krasny also motivated that, I think, I met Krasny and told him, I remember, I never asked him that, but I think that you skip that point because we learned in fluid dynamics, some of you have seen fluid dynamics with me, who hasn't seen, no big deal, is that this is a point vortex method, and the vortex does not generate a dynamics on itself. So I say, okay, I'm going to skip this point. I'm symmetric. I have a little window about, so it's a little bit like a Cauchy principal value, right, numerically speaking. And so, but then one can show that this method is order 1. So there's references and so on in this paper of my postdoc. So that was an order 1 method. Then the integration, there was just as a reminder for us, okay? So what did Pullen did, which is a paper I used, first paper basically I studied for my postdoc, because Pullen considered surface tension and did a very nice paper, I think. He saw some instabilities, which he couldn't claim if they were physical or numerical, right? He did that's very good. Some people, as I told you, claim things as doing the dynamics of numerics, right? Pullen said, look, I'm regularizing things 0, blah, blah, blah. It's not clear, not conclusive. Very nice study. And he was using a desingularization of the integral. Do you remember what a desingularization is? Right, so desingularization, let me write it for the 1 over x kind of case, just so it's like sort of like this. Remember, I wrote it wrong last time. I said, well, now it's recorded for eternity, 100 years. So desingularizations is when basically we do this. Right? I have to put the dx here and so on. Right? That's when you put all this together. Yeah, and then you desingularize, because if f has a derivative at 0, right, it's not a singular integral anymore. So there was a few strategies that I think Pullen tried too. I forgot. There was one called Van der Voer and whatever in here. And then we, with Greg Baker, following the idea of Shelley. So this is just a reminder, right? I'm not integrating Shelley nor Krasny. This is just the integral of Shelley was that, as Shelley was, alternate trapezoidal rule, right? That you skip every other point. I pointed to you last time. And Shelley did not invent this. This came from a paper by Sidi and Israeli. Okay? So this is a little bit the history of the problem. This is like 80-something, late 80s, late 80s. I think either late 80s, I think more like early 90s, okay? So this is more or less the history. But then, because we knew of this, by the time I was working on this, Mike Shelley was a student of Greg Baker, we knew that actually we had to use the alternate trapezoidal rule because it was the best way to integrate. And such a beautiful result by these guys, which is you just use an alternate grid and you get spectral accuracy with a trapezoidal rule, right? So do you remember what the alternate trapezoidal rule, or do you want me to sketch it for you? Right, it's just this, look. From your faces, it's just this. If I have a grid here, and let me say here, oh, these colors are not very good, particularly for the video. Let me put maybe, whoops, maybe the red one. Let me make different. So the alternate trapezoidal rule is if the singularity, if the kernel, right, blows up at this point, you use only the dots. And the spacing is 2h. Aye. And this is this is no big price to pay, right? You're just on the grid that's slightly bigger, but it could be exact if you're integrating something which is band limited, okay? So this is the alternate trapezoidal rule. If the singularity is on the dots, the red grid, then you just integrate using the grid on the white points. right? That's all there is. Trapezoidal rule. Super smart, super simple, super accurate. Okay? So what I'm going to start discussing today, and it's good to exercise things or refresh our memories and other things, is that let's consider now that our integral here and here we're doing it exactly. I mean, we're doing alternate trapezoidal rule, okay? And let's focus now only on the derivatives. And I want to tell you the stories of the derivatives, which then takes us to the Pullen paper, okay? So one thing before, let me remind you, if we're doing the Krasny problem was surface tension equal to 0, okay? So basically, this equation, nothing changes. These equations are slightly different because he uses this as the discretization. This guy is constant, blah, blah, blah. And then what Krasny does is basically to use this rule for the integration that skips a point, and he integrates this, I think if my memory is not wrong, Runge-Kutta, okay? Then, because these guys are expensive to compute, right? You don't want to, if you're using Runge-Kutta, you have to, at every time step, it's a one-step problem, you have to, at every time step, compute these guys, boom, 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 4 times. Remember, there's K1, K2, K3, K4, capital K, right? So then, we decided to do then, I think maybe Mike Shelley was already doing this, but Baker did it, the predictor-corrector formula. Because then it's also 4th order, Adams-Mouton, Adams-Bashforth, but you only have to re-evaluate these functions only once, because you keep the last 3 from the previous time step. Okay, story makes sense? Okay, now we wanted then to see if, there's the Krasny did the very nice study of Moore's conjectures numerically. He checked everything right, boom, on the money, right? That the critical time depended on the log of 1 over epsilon, blah. It was the curvature that exploded. How did he check the curvature also? Using the Paley-Wiener theorem. How? Doing the regression of the tail of the Fourier series, right? And you do it in the log way and so on. So if it's exponential, you see the decay and so on. Then people said, okay, Krasny showed that Moore was correct. The curvature blows up in finite time. So from the mathematical point of view, that was very nice, and using techniques, very nice to see things in the complex plane without using complex numbers. You see that a given type of singularity comes down, was like a branch point kind of thing. Mathematically very interesting, right, to understand the structure of this. And then people said, okay, let's go, and Pullen was one, I think, the first ones to do a serious work to see if surface tension, what does it do to the nonlinear problem? Because it was understood what surface tension did for the linear problem. It's right here. It regularizes the problem. Why does it regularize the problem? Because there's no unbounded growth rates, right? So in the Hadamard sense of perturbations being able to control small perturbations to your data, right? Now you have a control, because beyond these points, all the eigenmodes just oscillate because they're purely imaginary. Okay, you see the story from the mathematical point of view too, right? There's the engineering applications, physical point of view, but also from the mathematical point of view, people are interested. Okay, now we know that surface tension regularizes the problem from the linear point of view. Okay, all right. But the problem then becomes more complicated numerically, because this guy changes. You have to write here the nonlinear curvature in a parametrized form, right, in terms of parameter, and also because you want to control x and y, because this guy might and actually will sort of overturn, right? So you have to have something parametrized so you can see a function that's multi-valued. If you parameterize x of v and y of v, or x of s And y of s, if you're using arc length or not arc length, here it's not arc length, but it always goes from 0 to 2 pi. And the curvature is stretching, becoming, right, longer, right? But with this parametrization, you can model this overturning, right? Which is, that's the way how you parameterize also waves breaking, overturning, like the paper that Márcio is studying for his seminar, right? Okay, now, then the question that's where things started is, pooling was using, as I mentioned to you, and I'll refresh your memories very quickly, was using cubic splines for the derivative, which seems like a very good, very reasonable numerical method, okay? And I'm sorry, I think I hadn't put these on my notes in the web, okay, these things, so I sent it to you by email. Later on, I'll put this on the web if people want to download, because I think this is part of the class that I added at some point, okay? And then Poulin saw this. He saw that as this was happening, so this is Poulin, in Poulin's paper, okay? Poulin saw that right here, more or less, he saw that his profile was getting noisy, right? Was getting this sort of bad structure here. He tried to smooth it through polynomial interpolation, tried to do some tricks. He could not quite totally get rid of it in a satisfactory way. So he said, I don't know, it could be physical because of high oscillations, because of surface tension, it could be just numerical, right? And he was using cubic splines. So let me mention to you, where is it here? Oops. I wrote a little summary. Oh, here it is. Of cubic splines. Okay, so he used cubic splines. And right, let me quickly remind you of what cubic splines is. Okay, so if I have so I'm doing piecewise polynomial approximation. Let's see, what am I calling? F of x. And let me check with you. How many of you remember what cubic splines is? Or have seen? How many of you have seen cubic splines, even if you don't remember? Most of you. Okay, not everybody. So do you remember how it works? More or less? Okay, so let me do the review. That's what I want to do, but I don't want to bore everybody, right? So it's good. So let me go do very quickly. So here, I have this panel here. Let me put it like this also. So in this panel here of width h plus 1, okay, I'm going to set the polynomial sh So here's my cubic polynomial that sort of lives in here. Okay? And as I mentioned to you, if I have a highly oscillatory function or whatever, I do not want to use a polynomial of high degree, right? We mentioned, you guys, I remember some of you remember the Runge problem, right, of oscillations at the end. Okay. So I say, okay, so I'm going to use a cubic polynomial because we have here 4 degrees of freedom, which are the coefficients, right? We can ask for a C1 approximation, for example. So what is this? I can ask that my piecewise polynomial has continuous first derivatives. So we have for sure that it's an interpol, which means we have interpolation, but with interpolation of f of x. So if I say this just like that, right, and I don't say more, interpolation of f means at the nodes it has the same value of f, and it is C1. Not necessarily it will have the same derivative of f at the nodes, okay? Actually, we're going to even get continuity of the second derivative, which would be called the moment, m, capital M. I'll tell you why it's also called the moment, but doesn't mean that that second derivative is the same derivative of f. But, right, and actually, many times we don't even know what's the derivative of f. If the values of f, if it's not a grid function, if it's something we sampled experimentally, right, position of something, we don't even know what's the right derivative, but we know what's in principle, the points we have, so interpolation is the first thing we want. So it's C1, okay? So S prime is continuous, right? So this means S prime is continuous, where S, right, S is basically the polynomial which has components S1, S2, S3, or 4. That's my notation, okay? All right. And then it comes out that we have the following, right? If we write everything, we have the following. So this is exactly interpolation. Let me write it and then I'll tell you the story. Just a second. Okay, things for me to remember to comment to. So if we cook up this problem, and this problem, I would say that the moment comes maybe from structural problems. I think so. That's my impression. Structural problems. And this would be like a very simple beginning of a one-dimensional kind of, almost like a little finite element kind of thing, which is in each domain you approximate it by a polynomial. The moments have to do, just like structural engineering, which is if you bend a beam, right? The moments are the moments at the end, right? So that's why I think why the name comes moments, the second derivative, which has to do with the bending energy, okay, at the end. I mean, which with angles, and then you can write things, right? It's very simple to see that actually this is trivial to see, right? Just put x0, x equals to xj, sorry, over here, and you get zeros, right? And then you see all these other guys. C is actually the moment, the second derivative, divided by 2. You just differentiate this twice, you see that C is that, okay? Because you're going to get 2 equals that, and this guy's going to be 0, and the other ones, by differentiation, 0, right? And you can rewrite the whole system by looking at this. You can rewrite your whole system, AX equals B, in terms only of the moments, which are the C coefficients. If you know the moments, you're done. You know the polynomials. You already know this. You already know this. Here's the moments. You already know this. You already know this. You have then the polynomial. If you have your polynomial, right, and then of course you compute the first derivative as you wish, by hand or whatever, okay? Or second, I mean the second derivatives, if you're using here, you need the second derivatives. That's the CJs, right? If you're going to compute these guys through cubic splines. So that is cubic splines, okay? And you have a banded, that is the matrix is in band form. And why? Why is the matrix has this structure, which is good, which MATLAB, for example, takes advantage. You can actually tell MATLAB the structure of your matrix, so it takes advantage in algorithm, it saves space, and there are algorithms that are faster when you know a specific structure of a matrix, right? This matrix, well, you see that the MJs, right? Everything's written in terms of the moments, MJs. I mean, of a nodal information, the second derivative. It could have been the first derivative, who cares, for this question. So the moment at this node here is my chalk, tox is coupled to the moments at which other nodes? Just to neighboring nodes, right? I mean, we see here from Stark, these guys, look, this guy just appeared talking to this one. Of course, if you're only behind it, we'll talk to the other one. So basically, this has a banded and a sort of a tridiagonal kind of structure. Okay? So it's a good system to solve. You can do tricks and so on. It really doesn't matter here. Okay? So look what happened. Where's the... That's here. So look what happened. Let me make myself some space. Okay, so if you think that you're doing the integral basically exactly, okay, in particular for the linear problem, okay, so I have this written here somewhere. Oh, here it is, yes. Here it is. Let me go to the other board. So then, this is really the problem. That's the one we want to solve. But the problem we do, the numerical stability analysis, is this. So linear numerical analysis. So I have to write my system like this. Okay, where the notation, I don't think, oh, I'll write it just to be on the safe side. Okay? So what I've done is, this is the linear system, right? And before I had a tilde here, the notation here is just this. These are the solutions of the epsilon equations, okay? So now this is a linear system, okay? This is a linear system. Now I am using the alternate trapezoid rule. This is just notation that I'm skipping every other point. So if depending on where M is and J is, right? J is the singularity, right? These guys add to odd number. And now we can do first, let me do it here. Poulin cubic splines. So it's kind of a messy calculation, but Poulin did not do this in his problem, right, in his paper. So if you do this, this is what we got. So this is in our paper, we got this. Let me put two figures here. They're not going to be hand by hand as pretty as in the graphs I sent you. So this is the imaginary lambda and real lambda. Okay. So the imaginary lambda, so let me start with the real lambda. So the real lambda is like this. Okay, so this would be the exact sketch of the exact curve, right? So real lambda, let me come back to here. See, from this expression here, right? When k is below k star, this is always real. It becomes 0 at k star, and then it sort of grows a little bit as a square root as k is greater than critical. It's sketched over there. But then when we did our numerical stability, we saw this. We saw this. Look, we saw something like, let me sketch it for you. We saw something like this. Okay, this is a caricature. I've sent you nicer figures, okay? So what do I understand here? So this is Poulin's. I mean, that's not Poulin's fault. He did a very good method, the cubic splines. So doing the analysis of this, putting cubic splines here, and doing that, this is what we graph, and then we check on the computer, and it works very well. So what is this saying to us? It's saying the following. Look, let's start, because theoretically, we have that for a given surface tension is not too large, right? Just look at that formula over there. We have that some modes grow, real eigenvalue. Some modes grow, so the numerical method being on the yellow curve, what does it tell me? That the growth rate of these unstable modes is correct. In other words, I'm checking for dynamical instability and also for numerical instability. And I don't want to have any numerical instability. I just want to have a dynamical instability, and I want the numerical method to follow the correct dynamical instability, right? Remember when I started the course with implicit Euler had spurious damping, so it could also mask my true instability, right? So we want to make sure we have things right. So okay, so I start here. This is where my dynamical instability is. Okay, let me actually write this here. This is basically my dynamic instability, which is, I'm checking here, it's good, right? It's kind of on the curve. Modes that grow are correct. In other words, I'm checking for the eigenvalues of my matrix of the linear problem. And the eigenvalues here are very good. Okay? And then in this band here, let me shade it. In this band here, which is this band here, what do I see? I see that actually surface tension did the proper cutoff of the instability, because boom, the eigenmodes, the eigenvalues became purely imaginary. So they became oscillatory. Here, what do I see? I see, I would say, a certain error in the frequency. Because look, if this is imaginary, an imaginary eigenvalue is like a e to the I omega, right? So the frequency of oscillation of these numerical modes has some error that maybe could not be so relevant as if my true modes are here. These are just numerical modes that are oscillating in the wrong frequency. You follow what I'm saying? Right? Because look, our dynamics starts, our dynamics starts, so if this is E and this is Y, the perturbation, it's a sine of X. And if I'm doing and this is a good test I did that gave me insight in my postdoc, which is, I said, before I program those equations, let me program this equation and have full numerical control of this equation. Well, if I'm programming and I'm trying to solve this equation, and I put a sine as my initial condition, and I do a Fourier transform, an FFT, at all times, what should I see? Just a sign, right? Just plus 1, minus 1. And all the other modes are round off. And they will stay round off because there's no nonlinear interaction. So there's no production of higher harmonics using a different language for the same thing, right? In the linear problem, the principle of superposition works. If I have a sine of x, if I put in my initial condition sine of x plus sine of 2x, they oscillate. By superposition, they don't talk to each other. They don't couple. Okay? So, all right. So if I have sine of x, and this is k equal to 1, right? It would have the correct growth rate. Okay? And these guys here are already round off error that are oscillating at the wrong frequency. Sincerely, I don't care if the round off error is oscillating at the wrong frequency. You agree? Right? Little tiny guy oscillating wrong frequency. But when I cross here the red line, what do I see? Because this was because of the cubic splines. This is bad, and this is numerical instability. Do you agree? Because the theory tells us that from here on, look at the, right there, the Weber number. From here on, all the eigenvalues should be purely imaginary. All the modes, which would be round off, should be purely imaginary. Okay? Is the story making sense? I mean, if I'm saying anything that, or I'm skipping ahead of myself, stop me, okay? So therefore, you see, here's a problem where we have legitimate dynamical instability. Then things are okay. I don't care so much about this error. But then I get over this band here, numerical instability. This guy's bad. I want to get rid of this guy. But then before, so here's how the research went on this problem. So before I went to fix this, right, so here I said, oh, I think, right, talking to Greg Baker, I said, I think we know what went wrong with Poulin, right? He has this band of instability up here. So here in the notes that I sent you, the notes, you would see then, here's what I did. First, to see if why did I do this? First, because to do the splines analysis of this guy was quite messy, because you had to sort of put this information in here, do it by hand. It was quite messy. So I wanted to make sure that actually these graphs here were representative, that I didn't do any silly mistake, and they were, or even if I didn't do any mistake, that I did things right, that they were representative. So I programmed this with cubic splines, and this is what I saw. Look, let me try to reproduce the pictures for you. So you can follow my line of thought during the postdoc. So this is E, and this is Y of E, sorry. Y of V in time, okay? So this was my initial condition. And as time went on, I saw this. So what am I seeing? Is this okay, this graph? Yes. What function is this? This is just sine with a larger amplitude, because the amplitude satisfies the linear system of ODEs, and the amplitude is e to the lambda t, where lambda is real, right? So here, this is a simple function. I mean, it's still sine of x, because the problem is linear. In the nonlinear one, no, the guy starts tilting, so it's not sine of x anymore. And as it starts tilting, there's a high frequency production, higher harmonics production in Fourier space. Here, let me do the FFT of this guy. If I do the FFT of this guy, I see this. Here's k equal to 1. The other side, I don't have to see it, right? Because it's just conjugate. So here is k. Excuse me. So I see something like this. Let me do a sketch. Right? The axis maybe it's here because the log it becomes negative. Anyway, let me try to do this in a schematic way. Oops. Okay, this is the yellow one, this is the initial condition. Okay? And then I do it for these other two times here. Okay? And I get more or less the same thing, just maybe, let me exaggerate like this, growing the amplitude. Right? Can you see my drawing here? Oops, sorry. But what does this say? I just have one mode. All this is dirty. Okay? And then came the cool part. It was nice to see this. Then at a certain point, something cool happened. I mean, bad numerical, but cool because it's mathematical understanding. So there was a time that I saw this. Okay. So let me make this maybe in red. So we have a color code. So it was basically, it looked like a sine, and then you look in Fourier space, this is what you see. So what does that mean? Whoops, what is this guy here? This is n over 2. This is my highest mode is starting to grow. Why? Because it's let's say it's this guy here. Of my spurious growing modes, it's the one that grows. Let me exaggerate here. Let me maybe put it like this. It's the one that has the largest growth rate. Right? And then if I continue, I'll do one more picture. Okay, if I continue and put orange, this is still a sine. So orange came up here maybe. And then it goes like this. And I would see something like this. What am I seeing? So actually the correct picture is something like this. Right? It's a noisy profile. It looks like a sine superimposed with a noisy profile. What is this? It's a sine superimposed now with a small band of growing modes. And what is this band? It's this band. So this confirmed that, hey, I mean, I didn't think I'd do any numerical mistake here, even though it was very messy with the splines. But actually, the analysis captured correctly what was going on in the computer. Is it clear? Okay. So we said, well, cool. Now let's do the nonlinear problem. Let me put the graph here so you understand the story. Let me do the story for the nonlinear problem. Now here's the nonlinear case. Okay, so here it's again y. Here's y hat. Here it's e. Here's k. And this is what we saw. Okay, this is what we saw. For the nonlinear case, we saw the interface going like this. So now it's not a sine anymore. It's tilting. And then we saw actually for the nonlinear case, because I think somehow Pauling was putting minus sign. No, I don't even remember why we changed this, but this probably it's because of Pauling. So the figures were like this. It doesn't really matter. Oops, sorry, no, this is bad. So the linear one is just minus sign. And then it starts growing. Okay, so this is not a sine anymore. You agree? Because it starts steepening. Okay, if I do the FFT, like Krasny did, this is 1. So this is the yellow one. And then this is what happens. So you see what I'm doing? This is like a little bit like Krasny, right? So what's happening here? The waveband. This drawing is bad because I drew. So as this is the sign, here's in yellow, then the amplitude starts growing, but it starts tilting. Here's this one, it's already started tilting more. So as the profile tilts, it generates a band up to here, a band of wave numbers due to nonlinear interaction. Okay? Krasny had to filter this part here because it would grow. We didn't have to filter this part here because this part here is more or less in this region here at first. Right? Well, pooling was not filtering also. And this part here is just oscillating. It's not growing. Right? But then, when we got, let me maybe do the red one, there was a point where we saw this. I'm exaggerating the curve. It's not so big like this, okay? And then we saw a little bit of noise only here, similar to Poulin. And then we did the FFT, and we saw something like this. Okay, and then it was nice to see that actually what happened is that, well, we knew that this guy was linearly unstable. It continued growing in the nonlinear case. And somehow, because this part was growing too, it did an interesting modulation in the sense that the noise did not appear over the whole interface. It appeared more at the region where the curvature was large. And in a very similar way to, I think I drew this somewhere, over there in the beginning, right? Here. This was due to some, not easy to see, modulation with this guy growing and this band here growing, and this is numerical, right? And due to cubic splines, right? And it gave us a picture qualitatively very similar to what Poulin had. So basically, we were able to explain that cubic splines, right, what was not doing physically was that cubic splines was not seeing surface tension properly for high-frequency modes. In particular, for a band of high-frequency modes, there was effectively no surface tension, numerically speaking, because this guy was growing, right? And we could see here, surface tension was already making the frequencies wrong. Well, we didn't care so much, but the problem was that this band of frequencies here had a spurious numerical growth, and if it's growing, it's because it's not feeling surface tension. I mean, that's the physical interpretation. Why it's not really feeling, it's basically because of the discrete approximations, numerical approximations. So we said, okay, here's the first result from our study, right? But still, we wanted to publish that with something fixing it, right? Sometimes you can just publish explaining what goes wrong. But since we got this result, okay, in a good time, and the postdoc was long enough, said, well, let's now try to fix this. Okay, so now I'm going to explain to you in the minutes the class finished, how did we fix it? Okay? But please, ask me, is it nice? I want you to at least, even if you've not seen all the details, of course I'm not going to do this is messy. Even in the paper we don't do it. I mean, we just say it, right? That the growth rates are like this, like that. But I want you to see the story, right? And the story starts with a nice paper by Poulin, inconclusive in some part, enlightening in other parts. And we were able somehow to at least explain, and actually had a chance to meet with Poulin once, and he said, oh, that's very nice. I didn't see it happening this way. So boom, boom, boom. And we see things happening just like in his paper, right? And this taking place, right? Non-intuitive why this happens like this. But when we did the analysis and we checked, it was qualitatively the same. And then we said, okay, now let's try to fix this. Okay. Oh yeah, here's the paper. Yeah, but I basically didn't even. I do need something here. Let's see, where is it? Well, I know this part. I don't. It's okay. All right, so the way we did to fix this was to some extent simple, even though there was a headache at the end, which is we said, okay, so let me still use this system here. We said, look, you guys can help me. If I'm doing the integral with the alternate trapezoidal rule, and I have spectral accuracy, which is fantastic for the singular integral, how can I mean, I can compute the derivatives with spectral accuracy also, right? For the linear case, and of course, for the nonlinear case. Where does the derivative shows up? In the curvature, boom, boom, boom. Here, I can compute the derivative with spectral accuracy. How? Instead of using cubic splines. How? FFT, right? So this is just, see, I go to Fourier space, right? I go to Fourier space, and I'm not, for this guy, I'm not going to go to Fourier space twice, right? This guy, for example, let's compare this guy with this guy. I go to Fourier space, I get H hat, Y hat, sorry. So I go to Fourier space, I get Y hat, I multiply it by IK, and I come back, and I also multiply it by IK squared, and I get this guy. So I go to Fourier space once, and do 2 inverse FFTs, and I get this guy and this guy. Piece of cake, easy, right? Do the same thing for the X, and do once for the gamma. I get all these derivatives. Okay? So then I said, come on, this is simple, right? I mean, good, now I have a spectral accuracy. So basically, in space, if I think of this as an ODE, then we were very excited. We said, okay, let's see what happens. Because if I think of this as an ODE, and while my sine of x is band limited, so look at here. Even when the sine of x is already quite tilted, is this solution band limited? Yes, because spectrum ends here. All the rest is round off, right? So that means for basically, right, for the whole time during our computation, this right-hand side of this ODE from the method of lines is exact up to round off error, right? And we just got to take care, I mean, in terms of instability, if Krasny doing the filter, if it's zero surface tension, whatever. But if we do this correctly, we don't even need the filter. And basically, we're only going to have an approximation due to the OD, Runge-Kutta, or what we did, which is 4th order predictor corrector. Okay? Fine. But then there was a bad surprise that fortunately we were able to fix it, which is using, so now, Fourier differentiation, right? We got this. We got this picture. So can you see what this this figure is saying? So with the FFT, we got everything exact. Boom, 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 like here. Growth rates, perfect, tum, 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 okay? Up to the critical wave number. Then here, imaginary eigenvalues, exactly on the theoretical curve, but a problem at the Nyquist frequency. There was a red, this guy, so there was a numerical instability only. That was like, come on, we just missed this mode. God, we were like celebrating the goal a little bit ahead of time. It hit the post here for the highest frequency. That one did not go in. I said, come on, what happened here? What happened here? And I have time to finish. It will be perfect time to finish this dramatic moment of the game, right? So we were really happy, but we got everything, but this guy. And then I went to the computer and said, no. I'm doing something wrong. Let me see just if I have. Maybe I have this picture for you guys somewhere. I know how to do it. Well, anyway, but I'm going to show you what happened. So you put this on. I put this on the computer. Maybe I don't have the picture because it's very simple. So I have sine of x, and eventually sine of x becomes like this. Okay? This is E. This is y. And then we did the Fourier y hat. This is k. This is 1. You see something like this, goes like this. And only this guy grows. So it's really just the n over 2. So we see it in the computer. Actually, let me tell you the truth, actually. Let me tell you the truth. When I did the first time this graph, I said, no, it's right on the money, and I put this point over here. I said, Greg, we have it, and I'm just going to check in the computer. And then I checked in the computer, and I saw this, and I saw this guy growing. So I said, maybe I have a bug in my code. I checked. No bug. This guy, only this guy was growing. And because it's the linear case, it doesn't affect the rest, right? I didn't need the filter because all these guys were oscillating, and were oscillating at the correct frequency, right? So I said, what the hell is going on? So that took me a while to figure out. I thought it would, I knew it was not a bug, but then this is what happened. Look, this is what happened. This guy here, let me maybe erase this here. And I think I have time, yeah. This guy here, of course, was the problem. Why did I know? So here's where knowing the theory helps you to do the numerics. So I said, there's got to be something wrong with this guy. Do you guys see why I could smell fire here? See, that's where the theory helps. Look, this guy, the Nyquist frequency, is the only guy that's growing. And it was growing, it seemed to be growing exactly the same rate as the zero surface tension case. Okay? It kind of looks, I said, so maybe this guy here is not coming into the calculation. Why? So I checked. I thought it was a bug, right? I programmed wrong. I checked. I said, no, but it's working for the other guys. Why it's not working for this guy? I was going a little crazy for a while, right? For a few days, whatever. I checked it. Says, wait a minute. So look at this. Look at this. Remember that this guy here would be cosine of n over 2e, right? Because this is the Nyquist frequency for this guy in our stability analysis that we were doing Fourier stability analysis before. Okay? Well, And I know how to do the Hilbert transform. This is just Hilbert transform on the circle. And then look what happened. If I differentiate this guy and do the Hilbert transform, what will come out? Let's see. Good exercise for you to be done in 3 seconds at most. 1 second to differentiate this in your head, another second to do the Hilbert transform in your head, and the third second to tell me the answer. Sorry? Yeah, okay, good start. Right? Maybe it's your second, not the first, not the last. The second, why? Differentiate sine, differentiate cosine, it's a sine. Hilbert transform of the sine is the cosine. I wrote this last class, okay? So that's part 2, second 2 of the 3 seconds I gave you, right? And we know how to do the Hilbert transform exactly, right? But there's a problem. Actually, think of the first second. Differentiate this with spectral accuracy. What do you get? Differentiate this with spectral accuracy. What do you get? Sine. Sine of which frequency? Nyquist frequency, right? N over 2. What's the value of that sine on the grid? This is the sawtooth mode. +1 minus 1, +1 minus 1, right? What is the value of the sine on the grid? Zero. If I integrate 0, if I do the Hilbert transform of 0, what do I get? 0. I don't get back this cosine sawtooth mode. Right? So I said, I'm doing things right, but getting the results wrong because somehow of this aliasing. Okay? And then I said to myself, okay, got some minutes. Yeah, I got some minutes. I'll be able to tell you the story. I talked to myself and said, look, this is a periodic integration, right? I can shift it by half a grid size. The result should not change because it's a periodic integration. I can shift it by any value as long as I'm integrating over the whole period. Agree? I said, oh, okay, all right. And then I said, I got it. I got to see. I got to be able to see the sine, which is here at half the grid size, right? Because here the sine is going to be +1, -1, +1, right? And that's why the sine goes like this. It's 0 on the grid. But then I said, how can I see the sine? So if I shift this whole integral over there, okay, I see the sine on the yellow grid, but then as you said, I would see the sine, okay? And then I would do the Hilbert transform of the sine will give me a cosine, but then it's 0 on the yellow grid, on the orange grid. Very good. Because then the cosine, I said, I'm stuck. But then there was a trick. And that's basically how I'd say it to you. There was a trick because I say, I either see one guy or I see the other. How can I do it? Right? And the trick that worked was that actually you can, in Fourier space, think in terms of Fourier space, you can integrate, in Fourier space, you can differentiate and interpolate in the same hit and come back. How is that? Well, if you want to interpolate in Fourier space, you multiply your function by e to the I theta, where this theta would be half the grid size. If you want to differentiate, you just multiply by ik. Okay? And by doing these two things together here and so on, I was able to go and come back and see here the proper cosine, blah, 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 and all the other guys too. Because the other guys, if I do this for the other guys, it's not a problem. It's only for this guy. So that was the trick. So the trick here was to differentiate plus interpolate at the same time, right? And you can sort of do it as you're doing the derivatives and so on. And therefore, I got the method to be stable, right? To be stable. And for this integral here, only for this guy to come back correctly, I tested that in the linear case. I didn't see this growth anymore, right? I'm not giving you all the details of this, but it's somewhere in the notes or definitely in the paper. I was looking for the notes, maybe not in this part, maybe for the ones I sent you, maybe not the ones I printed for me, but maybe there's a little bit of this information for the ones I sent it to you through email just before the class. But there's definitely in the paper. So that did the job. And and how did I also check for the nonlinear case that this was working well? Then I did the following. Maybe let me come here. So to make sure, it's going to work for the nonlinear case, I did something that was, say, physically not legitimate physically, but mathematically. Okay, I did this. Look, let me put surface tension so large that all these guys here, right, are going to be purely imaginary, right? Or at least the spectrum is all. So then I checked it many ways. I checked it like this, and then you see that all. So I did very many tests, say with a sine, and it would grow, right? Or it would, some other cases, yeah, that's right. I put it very large so it would go, and everybody, only the first mode would grow, and all the other ones would be purely oscillatory, and we tested, and there was no growth whatsoever of any other mode, right? So numerically it was working. And eventually it would start overturning. But then, in our paper, we had to basically stop here a little bit because it was, and this is my final comment, and I'll mention one paper which then is very nice, which is these points here, and actually for those who've seen fluids, they're like Lagrangian markers, so they can move. So they're equally spaced in S, or in E, the parameterization, but not in space. So let me do an exaggeration. So for example, at one point, there's a lot of points here and less points here, right? And also this concentration of points here is a little bit why Bullen was seeing that noisy thing there. And this concentration of points here was a source, is a non-trivial source of stiffness. Because somehow it generates high frequencies and then there was a paper that became a very famous paper at the time. It's in the notes by Howe, Lowengrob, and Shelley. The same Shelley, Mike Shelley, very good. Sorry. Mike Shelley, which is Journal of Computational Physics, I think around 98. I have it written down somewhere here. I saw it, but now I forget where I put it. Well, I don't know, it's somewhere here. Well, it's because this paper is over here. Here it is. Oh, but I didn't put the year. I did not. Oh, no. I was sure I saw this. Anyway, it's somewhere there. I think it's 98, where they did a very nice numerical method where they would do a regridding at every time step. That means you change your points, whatever, so that these guys here were always separated by an equal arc length. Okay? And they removed actually the name of the paper is, I think, removing the stiffness and so on. And just by doing that, they removed the stiffness because the points were equally spaced in arc length. Okay? And their paper is super nice, super reference, but it was more or less done at the same time as ours, but they had to filter the Nyquist frequency. and they were using a spectral method also. They had to filter the Nyquist frequency because of that problem I just explained. They would not see surface tension. But nevertheless, a beautiful paper, and they had to change a little bit the formulation of these equations here so that the parametrization was not, say, from 0 to 2 pi. It was always through equally distributed in arc length. That removed the stiffness. Okay? Let's see if I have any more comments. No, we're close to the end. So that's more or less the story for this part. Okay? And according to my plans, next class, I will talk about finally the announced Poisson summation formula. And Poisson summation formula gives room for us to talk on that's this from Trefethen's book, on the discrete Paley-Wiener theorem, which is the definition, according to my understanding, and that's very nice from Trefethen's book, is the proper, very clear definition of spectral accuracy. Is when you put Paley-Wiener together with Poisson summation formula, which is the aliasing formula, and then you get that, okay? So here I end, at least it's good, I end a story of a numerical, more high-level numerical study where you have numerical instability that you want to eliminate because you have dynamic instability, which you want to understand, and so on. And it teaches us many things like alternate trapezoidal rule and other things. Let me finish because there's another class now.